Hi, welcome back. In this video, we're going to talk about the squeeze theorem. The squeeze theorem is very useful in helping us to find the value of a limit if we can't solve it either algebraically or graphically. In my previous video over special trig function limits, we defined the limit as x approaches 0 as sine of x over x as just being 1. But what if we couldn't solve this algebraically or graphically? So we need to use the squeeze theorem. This is where the squeeze theorem is very useful for us. So let's take a look at this right here. For this one, I'm going to draw a unit circle. And from my unit circle, at x equals 1, I'm going to draw a vertical line, just going straight up there. Okay. And I'm going to draw a line kind of connecting the two from the origin right here. And what I want to do is I want to look at the area of this sector. Now, I know from pre-cal last year, to find the area of that sector, it's just going to be pi r squared times the portion of the circle that is used for us. And of course, that's just going to become x over 2 pi, the part of the angle over that. So that's that part of the angle. So theta is theta over 2x, 2 pi, which I am using just x here. Canceling out the pi's, area of a sector is just, what's that, 1/2 xr squared. And we know the radius of the circle is going to be 1, so it's just 1/2 x, or x over 2. So that's going to be the area of our sector right there. But let's talk more about this area. So we want to take a look at the area of this sector. Now, I know the area of the sector is going to be between two areas of a triangle. For example, I have this really big triangle right here. And I know that this length is 1. And from right triangle trigonometry, this is just going to be the tangent of x, if x is our angle right there. Well, we're using x for theta. So this right here is, so the height of this triangle right here, this side right here is just going to become the tangent of x. And again, this has a length of 1. So this big triangle's area is much larger than the area of the circle, of the sector. So I know that the area of this large triangle is going to be bigger than the area of our sector. Now, I also have another triangle right here, and that's this triangle right here. Now, because this is a unit circle, I know that this length right down here is going to be the cosine of x, and it will have a height of sine of x. So if I wanted to find the area of this triangle, remember x is my angle, I can just use my rule. This is the area of my small triangle. So the area of my sector here that I want, the green part, is between the area of this smaller triangle and this much larger triangle. So now all I got to do is just plug everything in. Well, the area of the sector we just said was x over 2. Well, to get the area of the small triangle, that's just going to become that 1/2 cosine of x sine of x. That should look kind of familiar to you. It looks kind of like our double angle back from pre-cal. And the area of our large triangle is just going to become 1/2 the tangent of x times 1, so we just leave the tangent of x. So now I'm going to do a little bit of algebra. I'm going to replace that tangent of x. I don't like it. So I'm going to, well, first thing I notice, even better, oh my gosh, everything there is multipliable by 2. I'm just going to cancel out the 2. So I'm going to multiply through 2 by everything. And I'm going to get cosine of x, sine of x, less than or equal to x, less than or equal to tangent of x. Rewriting tangent of x, I can go cosine of x, sine of x, less than x, less than or equal to, less than or equal to. And what's tangent of x? Sine of x over cosine of x. And I'm going to flip everything. Well, I don't want to flip that. No, let's not do that. Okay, let's just leave it like this. So now the next thing I notice is, oh, look, everything is divisible. I can divide everything by sine of x. I'm going to go and do that. Divide by sine of x. And if I divide everything by sine of x, we get cosine of x less than or equal to x over sine of x less than or equal to 1 over cosine of x. And I'm just going to take my limits. Okay? Now remember, we want sine of x over x. That's what we want. That's what we want. But if I have x over sine of x, so it's not really quite the same, so I'm going to flip everything around. But be careful, when you flip everything, you flip your signs. So ironically, these all just kind of stay the same. So if I flip cosine 1 over, this becomes 1 over cosine of x, right? So let's go and write that out. 1 over cosine of x greater than or equal to sine of x over x greater than or equal to cosine of x. And I'm just going to switch everything around to get my symbols in the way I like them. And if you notice, we actually wind up with the same exact thing. So, and remember you saw in our last video that x over sine of x and sine of x over x are exactly the same. And we can kind of see that here algebraically as well. So now I'm going to take these limits. Let me take the limits here. If I take I want to find the limit as x goes to 0 of sine of x over x. I really don't know what it is, but if I notice, it is sandwiched in between cosine of x and 1 over cosine of x. This is my unknown. So if I can find the limit here of 1 over cosine of x and 1 over cosine of x, that might give me a hint about what my limit of sine of x over x is. So let's go ahead and do that. If we take the limit as x goes to 0 of cosine of x, that just becomes 1. What about the limit as x goes to 0 of 1 over cosine of x? Well, that's also going to be 1 because the cosine of 0 is just 1. So notice, we're now saying that the limit as x goes to 0 of sine of x over x is now between 1 and 1. So pick a number between 1 and 1. Of course, it's just going to be 1. So therefore, we can say that the limit as x goes to 0 of sine of x over x equals 1. And this is by what we call the squeeze theorem. Now, you won't be asked to do these drastic proofs like this on the AP, but it is kind of fun to see. Matter of fact, let's take a look at another example. This is a much easier one. What if we wanted to find out the limit as x approaches 0 of x squared times sine of 1 over x? Well, I don't know this, so I'm going to use the squeeze theorem. I know, but I do know that sine of 1 over x has to be between negative 1 and 1. That's just my rule. Any sine of anything has to be between negative 1 and 1. So if I now multiply everything by x squared, I would get negative x squared less than or equal to x squared sine 1 over x less than or equal to x squared. And now I take the limit. Well, the limit as x approaches 0 of negative x squared is 0. And the limit as x approaches 0 of x squared is 0. See, my ends, I know that those both equal 0. So therefore, I can now say the limit as x approaches 0 of x squared sine of 1 over x has to be between 0 and 0. So therefore, I can say that the limit as x approaches 0 of x squared sine of 1 over x is 0 by the squeeze theorem. All right, if you go to my next video, I'm actually going to show you how we do this in calculus.